So our next speaker is Steve White, and he's going to talk about the technical requirements for the Argus 144 receiver and its proposed digital backend.
So does that look good?
It looks great.
Okay. So yeah, so my talk is really going to be more of a perspective from how the instrument fits into the GPT parameters and what we've learned, and then some of the cost considerations really about so this proposal will fit into this MSI call for proposal. So I'd like to start out with just complimenting the original Argus team. They produced an instrument, even though it was sort of a student-driven instrument, grad student, it was really up to high standards, and it allows us to take what they initially accomplished and expand it. So, a lot of compliments to theirs for what they delivered. So, our working assumptions for this instrument is that we will replicate the original RF modules, and that means feed horns, mimic devices, which are 288 required, and the LNA modules. It's not clear to me if we'll need another source to build the modules, or if JPL takes that responsibility. But the strong point here is that JPL is responsible for delivering the mimics unless we find another source for them. The second thing, as Andy already mentioned, is revisiting the LO distribution and the YIG filter requirement. We have some ideas about that. Of course, with any expansion of the receiver is going to require a large doer. And one of the major concerns, I think, is the waveguide window. That size of window at this frequency really presents a lot of challenges. So I'll touch briefly upon progress we've made on waveguide window developments, specifically since this original proposal. I'll address some of the cryogenic issues and how we may solve those. Andy's already mentioned about the thermal loading problems, what goes along for a larger doer. And also talk a little bit about the IF modules and what we found with the current Argus system on optical receivers and transmitters, and how we might redesign the IF system to incorporate those. Design for the monitor control, there's no major changes except sort of migrated over to an Odroid type single board computer. We have experience with that with our ultra wideband feed development and X-band upgrade. And finally, our choices for the digital signal processing, we chose 600 megahertz because of the available parts at the time we made a proposal. And since we haven't really revisited that, that's kind of our working assumption. So a little bit about the Argus modules. And we've already seen the module, and this is a prototype, and the noise performance. And on the right is taken from Matt Seth's thesis. And if you'll notice, there's quite a bit of spread variance in the noise temperature measurements across modules. And there's sort of a low noise point at 108 gigahertz. Now, this is something I'm not a low noise amplifier expert, but I mean, it seems like there's room to maybe better select mimics to lower that variance some, especially if we need 288. So that might be, that might be even broader with those numbered elements. And I don't know if there's anything to be done about the amplifier design itself, and kind of input from astronomers would be helpful if the noise, if it would be better to have sort of a U-shaped noise temperature, you know, where the minimum is at the lower frequency. So that's just some points to ponder. This is Josh Gunderson's initial concept for the Argus cryostat, which gives you an idea of the size. It's really, this one, the original one was designed for a 2-foot hole. We'll have to go up to a 3-foot turret hole in this one. And the thing which gives you reference is the window size. And it looks like in his initial concept, you need like a 26-inch window. And I don't know if he has made initial cryogenic sort of calculations and come to the conclusion that you need 4 refrigerators to cool it adequately. But there's a lot of variables in that and a lot of work to be investigation to reduce the cryogenic load and just see what is really required before we make assumptions on the number of refrigerators required. So far as window development, our ultra-wideband feed project has similar requirements. So we went down the path of developing a vacuum formed window with quartz fabric and Epitech 301 epoxy. And so far we've demonstrated we know how to build these. We've modeled and strength tested an 8-inch window, destructive tested it, did vacuum tests on it, and it all conformed to what we predicted in the modeling. So we've jumped ahead and started making the ultra wideband feed window, which is 23.5 inches, which is not far from the 144-inch or the Argus 144 element, which requires at least a 26-inch. So we're close to making those size windows and doing tests on them. Also in the interim, we've made a 17-inch window for an NGVLA feed. So, but as you can see, there are some issues and problems to be solved. The thickness of the window and the dielectric constant generates reflections, and you can see that on the S11 simulation on the right, which is modeled with a 4mm corrugated horn. And the blue curve is without any waveguide window, and the orange is with a 6mm quartz window modeled with the Epitech 301 epoxy. You can see there's some reflections for that. So that's something that has to be addressed. And also the Epitech epoxy is loss tangent is higher than what can be used for noise temperature specifications at 3mm. But we know of Lisa Locke, who really, she started us on this path of investigating this. They did it with a pure material called tinkat, or I don't know how to pronounce it, but it's impregnated with syncate epoxy resin, which has actually a lower loss. Its loss tangent is comparable to quartz, but it's very expensive and it's toxic. So we went down this path with the cheaper version for the ultra wideband development. But the techniques will be very similar. You just have to have more caution using, and it's a lot more expensive, so you could make mistakes. So that's a possibility in the future for window developments. This is just a photograph of our NGVLA 17-inch window installed, vacuum pulled on it. You can see the nice sheen, which is one of the final version. You hand sanded and a final layer of epoxy applied. And the one on the right is a 23.5-inch window from the ultra wideband feed. And this sort of in its raw state, hasn't been mounted into a ring for vacuum testing or had that final layer of epoxy applied. So as far as cryogenic compressors, we build all our compressors in-house, which is sort of a good thing. That means we can modify them and measure them. And the current design is a 7.5 scroll compressor from Hitachi. And it has a mass flow capability of 89 SCFM. They did have proposed on their website at one time a 10 horsepower scroll compressor. So we know how to build and incorporate larger scroll compressors. The 7.5 horsepower will supply gas for 2 CTI 1020s or 5 CTI 350s. So if the Argus load can conform to those kind of numbers, then we can supply them with 1 horsepower or 1 7.5 horsepower compressor. But if there's more than that required, then we have demonstrated a scheme for combining the mass flow of 2 compressors. It complicates things. You have to have some control and whatnot. But there's we presented that in an ERSI conference. The scheme for we actually use 5 horsepowers, but the technique is the same, and we successfully supplied more refrigerators than was capable of 1 5 horsepower compressor. The question, currently the LO is supplied by 1 Agilent synthesizer. The noise floor was such that and a YIG filter was required, and that 1 frequency source had to be multiplied up to the frequency, W-band frequency, and with all the associated loss and number of ports on the splitters and IF or LO cables and whatnot. We started thinking about maybe a second option, which is using a modular frequency synthesizer, which has a less range, or maybe could cover the range without any multiplications. We'll just have to see what's available. And that would reduce the number of splitters and multipliers possibly. And it all depended upon the cost and specifications of what's available and ease of implementation. Of course, along with that, the software impact would be pretty large. There would be, you'd have to have managers and control on several different oscillators. They all would be phase locked to the maser. So, and they have the option of being phase continuous. So there are viable options, I think, for this path, but they just need to be investigated.
Steve, you have about 2 minutes.
2 minutes, okay. So the IF modules, I'll go over this briefly. They are 600 megahertz, and there is a question of whether we can include the laser transmitters. And the reason we know that is we did experiments with the existing Argus that compared the 8 stabilized links from the GPT with external modulated, and it turns out we can't tell any difference. So that really opens up the possibility of using laser diodes incorporated into the modules. And if you're doing that, you might as well think about designing your own photodetectors for the same reason, and also contemplate multiplexing the lasers to reduce the fiber count. In other words, using different colors. So with that, I'll go on briefly to the spectrometer. And the concept for the spectrometer is that we maintain the broadband capabilities of the original Argus and route the 16 IFs to the spectrometer, Vega spectrometer, and build 128 channels for independent of Argus to process the rest of the data. And our design is really cost driven. I mean, to stay in that 15 $1 million or less. The back end is a large part. So we settled upon 600 megahertz just because of the bandwidth capability and some scientific input. And it gives you about 4.5 kilohertz frequency resolution. And this is the proposed block diagram of the spectrometer. And there's been some work into selecting the ADCs and the FPGA technology and what. So it's more than just a block diagram. We actually costed it out and saw what was available at the time, at the proposal. So this really concludes, that's my last slide. So that kind of concludes my presentation. So thank you for your attention.
Thank you so much, Steve. So just a reminder, you can ask questions in the Q&A box and Steve will answer them live. If we don't get to them live, then you will get a response via just text. All the questions are anonymous. And so even if you can ask questions anonymously, but even if you don't, your name will not be on the recording. So we have one question. What is the balance between front end and back end costs?
So yeah, that's a good question. Most of the cost is, I would say over 50% is the front end. It's very expensive to build these modules. And with this concept, I would say we were probably 20% of the total or less using the 600 and the commercially available. And that was really the driver for selecting this particular scheme for developing the back end. It was just cost driven to keep the total cost so we could put more funds into the development and research. This doesn't really, the back end doesn't really require research. We know how to build it. It's just, so that it really eliminates labor and engineering time versus in the whole project.
So I'm again, shares prerogative, but if I wanted to have more than 600 megahertz of bandwidth, let's say make it a gigahertz, how much would that increase the cost or complexity?
Yeah, so that's a good point. This is based on 2-year-old really technology. So it may be at this point in time, or when we get funded, it really comes down to the ADCs. If there's an 8-bit ADC that can sample at 3 gigahertz and cost competitive with what we already proposed, that may be in the cards. But the kind of Casper development where you're talking 4 gigahertz is really cost prohibitive. So it's not out of question. We can expand it more than 600 by the time funds arrive, but it really is dependent upon what's commercially available.
Thank you.